Okay, so there's really only three types of signed numbers that we deal with. Two of them you probably won't actually see, but they're very good for learning. They're very good for learning. They kind of build up to the third type of signed number, which you actually will see. So I'm going to start with the ones that you probably won't see. The first one is called signed magnitude. Signed magnitude is actually the easiest one to explain. Really all it is we have one bit for the sign, and then the rest goes to the magnitude. So when you think about it, it's pretty easy to explain. I mean, it's also really easy to show. So we have the number over here. It's like 1001. Well, if we want to display this number as a decimal, we'll just take the first one. We know that this is going to be negative, and then we have the rest over here, which is going to be a 1. So likewise, if we want to show the positive form of it, we'll just do 0001. This bit is going to show that we have a positive number, and then the rest over here is going to show that we have a 1, so it's positive 1. And then this can extend to whatever we want. Now, the problem with signed magnitude is when we do addition, what happens if we add two numbers over here, which are, say, I'm just going to look at the magnitude right now, actually. Like, say we add the number 111 and then 001. Well, this is going to overflow. We get 1000. What do we do with this extra number? Does it go into the magnet or the sign for some reason? That doesn't make sense. That just kind of hurts the system. Or do we just lose some precision instead? So signed magnitude is limited by this sort of idea here, where we don't know what we're going to do with this overflow. And that also that in addition to the hardware being incredibly complex, like when we have to manage all of these things, like we have to look at a bunch of corner cases. We have to look when the positive number or when it overflows. We have to look at the times when the signs, like if we're doing multiplication, if the signs are the same, then we can make sure the sign changes. If the signs are different, then we have to do some other stuff. And it just becomes a giant hassle. So we need a simpler form, something that's easier to compute as far as the computer's concerned. And that's where we get the second form, which is the ones complement. Ones complement is computed in a single step. You just invert the bits. And like signed magnitude, the first bit still tells you whether you have a positive number or a negative number. But now, to figure out what the positive or negative form is, you actually have to compute the ones complement. And the way we'll do that is with an example. So say we have the number 1001. I'm now being super creative compared to this 1001 from above. So we know that in signed magnitude it's -1, but in ones complement it's different. We know that this first bit says that this is going to be a negative, but this part over here isn't going to be done in magnitude. We actually do the ones complement. Let's invert all the bits here. I'm just going to put a 1. So 0, 1, 1, 0. We know that this is equal to 6. So then what we'll do is we'll take this number and we'll put it up here. So the actual number is -6. And if we want to do it with a positive number and figure out what the negative form is, it's the same thing. So 0, 1, 1, 0. We know that this is equal to 6. Well, if we want the negative form of it, or we're transforming it to the negative form, we will just take the ones complement over here. So invert all the bits, 1, 0, 0, 1, which equals to -6, as we found before. Now, let's do one more example with ones complement. And this one I'm actually going to pick a little bit more carefully. Let's say we have a 1-bit number. And let's look at what is the ones complement of the number 0. Well, 0, if we invert all the bits, is going to go to 1. That just makes sense. Well, oh crap. We only have 1 bit available. So this is actually going to represent 0 as a positive number, and it's also going to represent -0. Okay? That doesn't really mean anything. We can only represent the number 0. That kind of sucks. So let's see what happens when we add bits to it. So let's look at 2 bits. We've got 0 and 0. Well, this is going to map to 1 and 1, but it's still -0 as far as we're concerned. 0, 0, 0. It's going to map to 1, 1, 1. Still technically a -0. We will always have the -0, and we're just losing a number there. So can we do better? Yes. And that's where the 2's complement form comes in, our third form that we'll see. 2's complement. So unlike 1's complement and sign magnitude, you will actually see 2's complement in practice. So sign magnitude you might see in some DSPs. It's rare, but there are occasions where it's useful. 1's complement, you are more likely to see Jared Leto riding a unicorn through campus. They just don't show up. 2's complement is way better for multiple reasons, and I'll show you those a little bit later. So the first thing that you do to compute a 2's complement number is you take the 1's complement. So you invert the bits. But then you do one more step on top of that. You add 1 to it. And this seems a little bit weird. You might be wondering why, but just bear with me. It'll all make sense in a few minutes. So in the 1's complement form, think of it as a number line. This number line has a positive 0 and a negative 0, and everything in this number line is split directly down the center, and it just keeps going this way. So this will be 1, 2, 3, negative 1, negative 2, negative 3 over here, and it branches both ways. Well, the 2's complement, we get rid of that negative 0 component right here. And we'll just have the number line, which will look like a standard number line. We'll have 0, 1, 2, 3, negative 1, negative 2, and so on. Well, when we take this number line and we wrap it around a circle, something really interesting happens. We have 0 here, we have negative 1, 1, 2, negative 2, and so on, all the way up until we hit this other halfway point, or as close as we can get to it. And this is this is very similar to the way that we treat regular unsigned numbers. These unsigned numbers, if we have like 4 bits, for instance, like say we have 4 bits, we can only represent 16 numbers, of course. And those numbers are going to be 0 through 15. So if we're representing the numbers 0 through 15, this number circle is actually going to go 1, 2, 3 all the way up until 15, and it's going to wrap around to 0. We'll never see 16. So in this case, it'll go 16 through 31, 32 through 63, and so on. And this pattern, they're all technically the same thing as this 0 through 15. And the reason for that is what we call modular arithmetic. Modular arithmetic is the same way that you would look at a clock. A clock, the hands go all the way up until noon, and then they just keep rotating around and doing the exact same thing they were doing before. So when we say 16 through 31, we're really saying that these numbers are congruent to 0 through 15 rather than equal to 0 through 15. And I'll show you a better example of that shortly. So let's start by doing some 2's complement, or taking some 2's complement numbers. So again, let's take the number 1, 0, 0, 1, and let's find the 2's complement of it. Well, we know that this number is negative again because this first bit, just like sign magnitude in 1's complement, this first bit still technically signifies whether we're looking at a negative or a positive. Since it's negative and we don't know what it is, let's take the 2's complement of it and see what happens. Okay, so first step, invert all the bits, 0, 1, 1, 0. Okay, same thing as before, we got 6, nothing special. Now let's do step 2, which is add 1 to it. So 0 plus 1 is 1, 1, 1, 0. So this is equal to 7. Okay, awesome. Now we can just move this 7 up here. So now we get negative 7 as this number. So this number actually equals to negative 7. And if we wanted to look at it another way, let's do another one, for example. Let's say we want to figure out what the decimal form of 0, 1, 1, 0 is. Okay, well this first one is a 0, so we know that it's going to be a positive number, and since it's positive, we don't actually have to take the 2's complement. We already know what it is. This is the form that we can understand easily. This is 6, positive 6. So really the only time you want to take the 2's complement number, for our perspective, is when we want to know what the number is as a decimal form. Otherwise, we can do something really, really cool with the 2's complement number. Let's try adding them. So I'm going to do something simple over here. Like, we already know what -7 is, so let's use, and let's see if we can add to 0. So let's do 1, 0, 0, 1. Okay, awesome. We know that this is equal to -7. Not -1, -7. There we go. And then now let's add 7 to it. So 0, 1, 1, 1, which equals to +7. Now let's just add these things the same way we'd add normal binary numbers, or binary unsigned numbers. Okay, 1 and 1, 0, carry the 1, 1 and 1, 0, carry the 1, 1 and 1, 0, carry the 1, 1 and 1, 0, carry the 1. Well, this last one, we've overflowed. We've only got 4 bits available, and this extra bit, we can't hold it in memory. We don't have enough space for it, so we just ignore it. So we get 0, 0, 0, 0, which this makes sense. -7 plus +7 equals 0. Yes! Awesome. Math works. Well, what happens if we want to treat these as unsigned integers adding together? So this over here is the signed version. I'm going to go ahead and just put a little box around it to make it nice and pretty. So there's the, whoops. There's the signed version. Now let's do the unsigned version. So let's add the same numbers. 1, 0, 0, 1, which this is going to equal to 9. And let's add 0, 1, 1, 1, which equals to 7. And let's add those two things together. Okay, so 1 and 1 plus 1, 0, carry the 1. 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 Well, we've got this extra 1 again, so we ignore it. So we just get 0, 0, 0. But this 9 plus 7 equals 16. Why does 0 equal to 16? It doesn't equal to 16, actually. It is congruent to 16. And that's where this modular arithmetic notion comes into play. We can only represent 16 numbers. So and since we can only represent 0 through 15 here, this 16 wraps around back to 0. In other words, they're congruent. And that's why unsigned numbers are basically the same thing as signed numbers. Signed 2's complement numbers, I mean. You can treat them the same way. The hardware can be the exact same thing. You can have the same adder, the same multiplier, the same, almost all of that. You just have to do a few things for formatting beforehand to make sure that you have it in the A plus, or sorry, that's hard to read. You have the A minus B form, which is equal to A plus -B. As long as you really maintain this form, you're good. But you can, this number, this B, could be just represented as another variable. And let's call that A plus C, where C equals -B. That's the same sort of idea as doing the 2's complement numbers here. They do nothing really special other than notation, kind of, it's more of a human readable style of doing something. And a lot of students, this causes a lot of confusion with students. So students like to come up and ask me, so hey Michael, I have a number over here. I've got 0, 1, 1, 0, 1, 0, 1, 1, 0. Is this a 2's complement number? And I don't even have to think about it. I just look at them, wait a few seconds, I say, yes. And then they ask me, what about this number? 1, 0, 1, 0, 0, 1, 1, 1, 1, 0, 1, 0, 0, 1, 0, 1, 1, 1, 1. Is this a 2's complement number? And I answer, yes. Are you just going to answer yes to everything I say about numbers? Yes. Because every number can technically be 2's complement or unsigned. It's really up to you as an engineer to decide. So if we're adding two numbers, you'll add them the exact same way, so you don't even have to worry. It's really when you're done and you're basically trying to decide, do I have, well, in this case it'd be 0 and 0, so that's not hard to tell. But suppose we got the number 15 and 1 for the output. -1. these are actually the same number. This would be this 2's complement form of it, and this would be the unsigned form, but these numbers will show up the exact same bit sequence. It'd be 1111 or 1111. And if you take the 2's complement of this, you just invert all the bits. 0, 0, 0, 0 plus 1 equals 1. So we get the negative 1. These two things, all you have to do is make sure that the final conversion is the same and the initial conversions are the same. And then you can just add them and do whatever you want with them. They behave the exact same way. So they will always technically be 2's complement form. And that's really how you should treat it. So unless otherwise specified, just do what makes sense. If you have two unsigned numbers and you get the bit sequence, just add it together and then say, okay, I've got these two possible numbers out. Does the problem ask for does it have any sort of subtraction in it? Nope, then it's probably unsigned. But I can see why there's a little bit of confusion, but really, as long as you realize that they're the exact same thing, you can honestly just ask the professor to ask, do you want the signed output or the unsigned output? And that's really all there is to it. The rest is up to you. It's not a big deal. But there is one interesting thing about 2's complement numbers, and I'm going to just come up here and make a little bit of space. So let's take the number 1000, still having 4 bits that we want to look at the 2's complement of. So let's take the 2's complement of this. So we know the first step, 0, 1, 1, 1. Okay, awesome, we inverted the bits. Now let's add 1 to it. So plus 1. Okay, 0, carry the 1, 0, carry the 1, 0, carry the 1, 1. Oh, crap. Question mark? We got the exact same thing that we started with up here. Well, this is the one special case that actually differentiates 2's complement from 1's complement. And it's actually, despite it being weird and annoying, it actually makes it really easy for us to remember things about 2's complement. So remember, we always, by convention, we want this first bit to tell us whether we're looking at a positive number or a negative number. So this thing, if we want to tell whether it's a positive 8 or a negative 8, it's easy. We just say, by convention, this is equal to negative 8. Now we don't have to change the hardware or do anything special. It will always be negative 8. We can never actually represent positive 8. And that might be a little worrisome, but it's not. It's really not. Because in the 1's complement form, we have two numbers that represent the same number. We've got 0 and negative 0. In this case, we don't have that problem. 0, there is no 2's complement form of 0. So if we have 0, 0, 0, 0, we invert all the bits, we get 1, 1, 1, 1, and we add 1 to it, we're going to get 0, 0, 0, 0 again, which is what we want. In this case, we have a negative 8, and there's no possible way we can get a positive 8. So the only numbers we can represent are actually negative 8 all the way up through positive 7. And this is beautiful. This is math working with engineering. We don't have to worry about more things. This limits problems down the road that we would normally see with 1's complement. And it's nice because it also makes it easier for us to compute these bounds whenever we're thinking about arbitrary numbers of bits that we're going to look at. So say we have n bits in our integer. So we know that there's going to be 2 to the n possibilities, which in this case would be, we've got 16, if we have 4 bits, we have 16 numbers available. We can divide that space by 2, which is going to equal to 8. So I'm going to do 2 to the n divided by 2 here, which is the same thing as 2 to the n minus 1. And then this basically says, this is the biggest number that we can get in the space, so we know that that size is going to be the negative of it, so negative 8. And then all we have to do, for just ease, is subtract 1. And you get the positive side, which is going to be 7. Same thing over here. We can get 2 to the n minus 1, and I'm just going to go ahead and write it down here. 2 to the n minus 1, inclusive. And then if you want to find the positive, and actually we have to take the negative of that. If you want to find the positive side in your bound, you just do 2 to the n minus 1 minus 1. So 2 to the n minus 1 minus 1. And those are the total bounds that you can get within this particular space. And this is something that shows this is also another point of confusion with students. A lot of times people will ask me, so Michael, I'm not really sure what the bounds are on our system. As long as you remember that this 2 to the n minus 1 part can only get the maximum negative number, like you can, like let's just look at a 5-bit sequence, for instance. Say I have 5 bits. What is the largest number that I can get with that? So 2 to the 5 is equal to 32. So let's divide that by 2. Equals 16. Okay, so let's look at this. How do we represent 16 in binary? It's actually just 1 and then 4 zeros. Just like 8 over here, it's going to be 1 and then 3 zeros. And really, when you're doing that, you're just going to say, oh, I've got 1 more 0. You're just going to append a certain number of zeros, and there's just going to be a single 1 at the end. And no matter how many bits of zeros that you add to the end of this, if you take the 2's complement of it, you invert all the bits, step 1, so you get 0, 1, 1, 1, 1, and you add 1 to it for step 2. Give me 1 sec. And let me just move this out of the way. So, invert all the bits, then add 1. You will always get the exact same number that you started with, which is 1 with the particular number of zeros out. So you can say, oh, I know that this is always going to be the negative. So it's going to be negative 16 up through positive 15. There's no way I can get a positive 16. So let's just do 16 minus 1. Yay. Easy. And it really is that easy. It's not, that's what makes 2's complement amazing. Converting to and from 2's complement, there is a source of error with humans. It's not as intuitive as signed magnitude is for us. However, when we implement this in hardware, it is so incredibly easy for a piece of hardware to compute that it makes up for, by far, any sort of unintuitiveness that you might find with the conversion. And that's why we use 2's complement, and you will almost always see 2's complement compared to everything else. So, moral of the story is 2's complement is awesome. And it's really no different, or you will at least not treat it any differently than unsigned integers, other than when you want to convert between the positive form and the negative form. That's about it. Thank you. I'll see you guys next time.